All right, in this video I want to deal with a situation of equilibrium, specifically static equilibrium, although the same technique can be employed with dynamic equilibrium. The problem statement is, a sign weighing 357 newtons is hanging from a ceiling by two wires. The wire on the left makes an angle of 35 degrees with the ceiling, and the wire on the right makes an angle of 41 degrees with the ceiling. The two questions are, if the sign is stationary, which wire will have the greater tension, and then what is the tension in each wire? In this problem-solving process, the first step, as it is always with forces, is to draw a diagram showing all the forces acting on the object, in this case, the sign. Right, so we begin with a diagram here. Once again, as always, it does not have to be great art. We just have a little representation of the sign hanging from the ceiling with the wires at their designated angles. And now we consider the forces acting on the sign. There are three of them. First off, we have the tension in the right-hand cable, which we will label TR, the tension in the left-hand cable, which we will label TL, and the weight of the sign, which we shall label as W. So these are the three forces acting on the sign, going in approximately their proper directions. Notice I'm making the diagram big because it's about to get very crowded. Step 2 in this problem-solving process is to develop a coordinate system. What does X and Y mean? What does positive and negative mean? In this case, we can use a traditional Cartesian X and Y coordinate system where X is horizontal and Y is vertical. Since the entire goal is for the sign to remain stationary, there is no strategic direction to be positive or negative. We can just arbitrarily say that to the right is positive and that upward is positive. There's no compelling reason to do otherwise. So we've established our coordinate system. Step 3 is, given the coordinate system, do any forces need to be broken up into components? If so, draw those components and write out formulas for those components. Well, looking at our diagram here, we see that only one force is purely vertical, and that's the weight force. The other two forces do indeed have horizontal and vertical components, and we can draw those components. We can say that TR has an upward component, right, which we can designate as TRY, and a rightward component, which we can designate as TRX. And that the left-hand cable has also an upward component, right, which we can call TLY, and a leftward component, which we can call TLX. All right, so we've drawn our components, remembering that the components make right angles with each other, as always occurs with X and Y, so we have ourselves a couple of right triangles. That will be valuable to us as we now move on to the next part of this, which is to write out formulas for those components. Looking first at the right-hand side, we can begin, as we usually do, with the sine function, with the angle in question being 41 degrees. The formula for the sine function is opposite over hypotenuse. And looking at our triangle here, we see that opposite the 41 degree angle is the y component, TRY, and the hypotenuse is TR itself. We multiply both sides by TR. That will eliminate our fraction here and give us our first formula for the y component of the right-hand tension force, TR sine 41 degrees. We now look at the cosine function. The cosine function is adjacent over hypotenuse. Looking at the triangle, we see that the x component, TRX, is adjacent to the 41 degree angle. So that's what we put there. and the hypotenuse is once again simply TR. Multiply both sides by TR to eliminate the fraction, and we get our second formula, this one for the x component of the right-hand tension, TR cosine 41. We can construct similar equations for the left cable components, beginning with the sine function, except this time the angle is 35 degrees. Sine of 35 degrees is opposite over hypotenuse. Looking at the triangle, we see that the side opposite the 35-degree angle is TLY, and that the hypotenuse is TL itself. Multiplying both sides by TL eliminates the fraction and leaves us with this formula, TLY equals TL sine 35. Finally, we turn to the cosine function, which is adjacent over hypotenuse. Looking at the 35-degree angle, we see that the side adjacent to the 35-degree angle is TLX. The hypotenuse is TL. As we have done before, multiply both sides by TL. That eliminates the fraction. And now we have our final component, TLX equals TL cosine of 35. So step 3 is completed. We have found components and the formulas for those components. Step 4 in this process is to add together the x components and add together the y components, realizing that since the sine is in equilibrium, those components in both the x and y directions will add up to 0. So looking first at the x forces, we say the sum of the forces in the x direction, we have two of those, TRX and TLX are our two x forces. They're in opposite directions. TRX is pointing to the right. That is our positive direction. TLX is pointing to the left. That is our negative direction. So TRX gets a positive sign. TLX gets a negative sign. And those two forces must add up to 0 because the sign is not moving to the right or to the left. It is stationary in the x direction, so those forces must add up to 0. This can only be true if the two components are equal to each other. Notice, this does not mean that TL equals TR. No, it just means that TRX equals TLX. The x components are equal. This does not necessarily mean that the forces themselves are equal. Let's take a look. Going up here, we look at our formulas for the two x components. We put those formulas in for TRX and TLX. At this point, let us solve the equation now for TR. In other words, let's divide both sides by the cosine of 41. That'll eliminate that, and then we get TR all by itself. TR is going to be TL times this quantity right here, cosine of 35 degrees divided by cosine of 41 degrees. Plugging those figures into the calculator, we find that the quantity in brackets is 1.085. This immediately tells us which of the components is greater. This tells us that the tension on the right is greater, because we can say the tension on the right is 1.085 times greater than the tension on the left. It's not much. It's only about 8.5% greater, but the tension on the right is going to be a little bit greater. This is, of course, due to the difference in the angles. If the two angles were equal, the two forces would be equal. They're not, so we have to figure out which one is greater, and here we have done that. We know, without even calculating the tensions, that the tension on the right is a little bit greater than the tension on the left. This is going to come in handy now as we look at the sum of the forces in the y direction. There are three forces in the y direction, TLY, TRY, and the weight force. Notice that the first two of those forces are up, and so TLY and TRY are going to be positive. However, the weight of the sign is downward, which will be negative. Still, those three forces have to combine to 0 because the sign is not moving up or down. That tells us the y forces are in equilibrium. Now, the only way this can be true is if TLY plus TRY equals the weight force. Notice, again, I'm not saying that these two forces add up to the weight force. I'm saying that these two components add up to the weight force because it's these two y components that are working together to balance the weight force. Well, we use the formulas that we developed up here, and we say that TLY is TL sine 35, and TRY is TR sine of 41. And the weight force in this case is 357 newtons. It would seem that we're stuck because we still have two unknowns, TL and TR, but if we look over here, we discover that we have an expression for TR in terms of TL. So we take advantage of that. We say, all right, well, this side is TL sine 35 degrees, but this side is TL times 1.085 times the sine of 41 degrees equals 357. Now we use our calculators to figure out what the sine of 35 and the sine of 41 are, and we get to this point. TL times 0.5735 plus TL times 1.085 times 0.656 equals 357, because the sine of 35 is 0.5735, the sine of 41 is 0.656. So we multiply these two numbers together, and then we combine these two terms. And that gives us the result that 1.285 times TL equals 357. Because this added to this times this is 1.285. Dividing both sides by 1.285 isolates TL and gives us the value for TL 277.75. We would report this as 278 newtons because the problem has three significant figures. Well, now that we know the tension in the left, we can take that number and bring it over here, plug it in right there. And so TR equals 277.75 times 1.085, and that's going to be 301.36 newtons. Notice that indeed TR is greater than TL, as we discovered earlier on. So the answers to the questions are: the right-hand tension is greater than the left-hand tension, and the individual tensions are: the tension on the left is 278 newtons, and the tension on the right is 301 newtons.